After learning the definition of a subgroup, now let's talk about how can we determine a certain subgroup of any given group. Of course, we know that first and foremost, here are the conditions. First and foremost, we know that a certain H, let's say H, to identify that whether H is a subgroup of G, we must know or identify that H is actually a subset of G. This means H must be a subset of G. And take note that G must already be a group so that H could be moving forward and whether it's a subgroup or not. Okay? So take note that G is already a group, okay, so that we will be guided with the rest of the steps. So this is the first thing that we need to identify. It should be that the H is a subset. So it should contain elements, maybe not all, elements of G. Now, aside from this, there are also other things that we need to consider that we have in order for us to say that H is actually a subgroup of group G. There is actually a theorem for this, and let me write this in a theorem. So, a subset H of a group G, okay, it's a group G, is a subgroup of G if and only if the following criteria are met. I'm going to label this as second double I because I already took right here, I mean simplify, or because I have emphasized already that it should be a subset, okay? But definitely in this theorem, this will be the first thing that we need to consider. So I'm just going to write is a double I, okay? So H is closed under the binary operation, okay, of G. Okay? Because for a certain subset to be considered to be a group as well, so the closure property should be actually satisfied as well. The third one, but specifically it should be the first. But then again, pardon with that, I have written here the first to be considered. Okay, the identity element. Okay, E of G. Okay, must be in H as well. So the identity element that should be found in the subset must be the same identity element on the given set or the group. Take note that if we're talking about the identity element, we have already discussed that there is a unique or the uniqueness of identity element, meaning if H is already a subgroup, that H should have an identity element, right? In that element, since an H is since a subset of set G, the same identity element must be presented there. There should be no way that there is an identity element in the subset H or the subgroup H but different from the identity element of the bigger set G, because it would actually violate the uniqueness of identity element. And the last one, the third one supposedly for this theorem, but then again the fourth one to be considered is for all A element in H. Okay, it is true that the inverse must be in H also. Take note that all of these elements we're talking about are already elements of G, and G is already as a group. That would mean if we have a certain element in G, its inverse is also a part of G. Now, if we consider that same element as part of the subset H, for the subset H to be considered a group, it should also contain the inverse of that element A, same inverse on G. Okay? So that is for all A element of H. So this is how we determine the subgroups of a group. Okay, first and foremost, it should be a subset. I have noted that here because sometimes this is actually disregarded, but it should be like that. And the first consideration is closure property, existence of identity element. Sorry for that. Existence of identity element and existence of our inverse element for all element in H. Now, the only property that is not necessarily explicitly written here is the associativity. But nevertheless, since all elements are already found on set G, which is already a group, it is already understandable that the elements that are taken by subset H, the subset of group G, must also possess associativity. That's why it doesn't necessarily be explicitly written here. So we just need to have something like this. To add, aside from these conditions or considerations in determining the subgroups of a certain group, there are also additional concerns that we need to determine. Okay, when we talk about subgroup, take note that H is a subset of G, and of course, H could be equal to G in itself. Okay, that would mean the following could also be considered as subgroups of G. In short, these are the possible set H that would be considered a subgroup of G. Number one is G itself. Okay? Because it is possible that our H is actually equal to G, meaning all the elements in group G is also are also elements of the subset H. And since we know that subset could also take all elements of a given set, so G in itself is also considered to be a subgroup. This is what we call as improper subgroup. Okay? So we also consider that as one of the following subgroups. If you're asked to identify how many or list, don't forget to list the set G itself. Second here is this is what we call as the trivial subgroup. It's actually the set containing your identity. This is what we call as a trivial subgroup. This because this set alone, which is also, take note that E is an element of G. So if E is an element of H as well, okay? So for this case, since we only have one element here, if we're going to operate, okay, in any operation, binary operation star to itself, since it's an identity, it will just return to itself. And don't forget that in the proof of identification of the uniqueness of an identity, we were able to establish that if there exists E and E inverse element of a certain set, let's say set H here, it would actually tell us that they are just the same because of that specific proof. You might want to review that as well. This supports the idea that for this specific set or subset, which is a set containing the identity of G, the existence of identity element and its inverse already there. Now, associativity, since we already have established that even if you're going to operate this differently with different association of groupings, it will always be resulting to the identity itself. So, and of course, it's a non-empty set. So basically, this is a trivial subgroup. It's a set containing the identity itself. So if you're asked again about giving two, even if it's just one subgroup of any group, you can just simply identify the identity element, make it form as a subset, and that is actually considered as a subgroup. And the last one, or we have here the consideration for the non-trivial subgroups, okay, which are all H that are not the same as set G. So this point here, at this point, this is where your theorem here and considerations are considered. So if you're going to determine the non-trivial subgroups, always consider closure property, existence of identity element of G in that H, and of course for all given A in that H, there exists their corresponding inverses. So this is just additional concept here that we need to understand, because later on we will have examples and illustrations of determining subgroups. So basically, later on, if you're asked about to identify subgroups of a certain group, automatically the group itself and the set containing the identity are already subgroups of that. Okay? So that's all for this. Hopefully you'll be guided in the next few videos. Thank you very much for watching.